All right, today we are going to unpack the clever and I mean really simple logic behind one of machine learning's most useful tools, the naive Bayes classifier. We're going to get into how computers can make these incredibly smart guesses, even when they don't have all the facts. So it all kicks off with a question you've definitely asked yourself at some point. How on earth does my email filter just know what's junk? Is it some kind of magic? Well, not quite. It's actually a fascinating probability puzzle. But here is the catch. The perfect way to solve this puzzle, I mean, the mathematically flawless way, is so ridiculously complex and expensive for a computer that it's just, well, it's practically impossible to do in the real world. And that's really where our story begins. So let's dive into this impossibly big puzzle. We're about to see exactly why trying to build that 100% perfect spam filter would bring even the fastest supercomputers grinding to a halt. Okay, think about it like this. A perfect filter would need to calculate the exact probability that an email is spam, given that it contains the word prince and lottery and urgent all together at the same time. It has to understand how all these words play off of each other in every conceivable combination. And this whole concept has a name. It's called joint probability. It's just the chance of multiple things all happening together. So we're not just looking at the odds of prince being in a spam email, we're looking at the odds of that entire phrase showing up. And this right here is the killer. For every single new word you want the filter to recognize, the number of combinations it has to calculate just explodes. It grows exponentially. We're talking about a curve that basically shoots straight up into the sky, which makes this perfect approach a complete non-starter. So if the perfect way is impossible, what do? Well, this is where it gets really clever. We make an assumption, a naive assumption. And this one simple idea, it changes the entire game. So the perfect but impossible way assumes every word influences every other word. But the naive way? It makes this incredibly bold and, yeah, technically incorrect assumption. It just pretends that every single word is completely independent. It assumes the word prince has absolutely no statistical relationship to the word lottery. And this quote nails it. The naiveness is that exact assumption, that all the features are independent. We know that's not really true in language, but by pretending that it is, we unlock a massive, massive shortcut. And that brings us right to the math shortcut. Let's see how this one naive little idea takes that exponential nightmare and turns it into a simple, manageable, linear problem. Okay, just look at these two formulas for a second. See the top one, the perfect method? It has n, that's the number of words, up in the exponent. That is our exponential explosion. But now look at the bottom one for naive Bayes. N is just a simple multiplier. That's linear growth. It's the difference between a rocket launch and a steady walk. Right, I know, those formulas can seem a little abstract. So let's ground this with a super simple example. Let's just imagine we have two categories or classes, spam and not spam, and we're only looking at two features. Let's say two words that can either be there or not there. And here it is. This just brilliantly shows the difference. Even with this tiny, tiny example, the perfect way needs 7 different parameters. The naive way only needs 5. Now just try to imagine scaling this up to thousands and thousands of words. The savings in computing power become absolutely astronomical. But, this naive approach isn't a perfect silver bullet. It has its own quirks. Let's talk about a really common hiccup called the zero problem, which is what happens when our model stumbles across a word it has never, ever seen before. So here's the deal. If our spam filter is reading a brand new email and it sees a word like, crypto bonanza that it never saw when it was being trained, it's going to say, well, the probability of this word being in a spam message is 0. I've never seen it. And because the whole naive Bayes calculation involves multiplying all these word probabilities together, well, what happens when you multiply a long string of numbers by 0? The entire thing becomes 0. A single new word could make the email look totally harmless, even if it's packed with words like prince, lottery, and urgent. The whole model just breaks. Luckily, there's a really elegant fix called Laplace smoothing. You can think of it like this. We're basically giving the model a little bit of imagination. We add a tiny virtual count to every single word in our vocabulary, basically pretending we've seen each word at least once. This makes sure that no probability can ever be exactly 0. And here's how simple it is. Really just 3 steps. First, you count up a word's appearances like you normally would. Then you just add one to that count. That's our little virtual citing. And finally, to keep all the math fair and balanced, you add the total number of unique words to the number on the bottom of the fraction. It's a simple trick, but it's so powerful. Now, there is one other little practical issue to deal with. It's called numerical underflow. When you multiply tons and tons of tiny fractions together, the final number can get so infinitesimally small that a computer's memory just rounds it down to 0. And we're broken again. The fix is another clever math trick. Instead of multiplying the probabilities, we just add their logarithms. This turns a risky multiplication problem into a much safer addition problem. So after all these little tweaks and clever fixes, we get to the big takeaway here. The naive Bayes classifier is simple, for sure, but it is definitely not stupid. Let's wrap up by looking at why this naive approach is so incredibly powerful in practice. I mean, the advantages are just huge. It's blazing fast to train and to use. It performs shockingly well, especially for things like sorting text, like our spam filter. It doesn't need a gigantic mountain of data to get going. And maybe best of all, the logic behind it is simple enough that you can actually pop the hood and understand what it's doing. And the results really do speak for themselves. In some areas, the performance of this simple, naive little model is right up there with these huge, way more complex things like neural networks and decision trees. And that is truly remarkable. Which leaves us with a final thought to chew on. By making a deliberate, simple, and, slightly wrong assumption, we unlocked a solution that's fast, efficient, and incredibly powerful. It really makes you wonder, doesn't it? When is being just a little bit naive actually the smartest path forward?